Good afternoon, Muthu.
Hi, Ganesh. Good afternoon.
Yeah. Dr. Sriram and Vinay. Oh,
yeah.
yes.
Yeah, Ganesh.
Yeah, so slowly people are coming, I think.
Yeah.
Okay. I see that.
Time.
Hi, sir. Good afternoon. Vinay here, actually.
Good afternoon, Vinay. From the auditorium.
Let's wait for a couple of minutes. The students are like, they are repeating it, actually.
Okay, sure. No problem. Sure. Okay, Muthu, let's wait for a couple of minutes.
Yeah, sure, absolutely. No problem.
Thank you.
Thank you.
Mr. Muthu Muthiah is going to present over spectrum scale features. To introduce him, Muthu Muthiah is an architect with IBM Systems Group Software Defined Storage Organization. Muthu's 20 years of industry experience has been focused in the areas of storage, systems, and platform management. His current area of focus centers on enabling IBM's highly parallel distributed file systems on the cloud. In addition, Muthu also serves as the architect responsible for the installation and deployment of this distributed file system as a storage-defined storage service. Muthu has a master's degree from the University of Oregon with a specialization in multi-cache networks. He currently holds 6 patents. So shall we welcome him with a round of applause? So hi, sir, over to you.
Thank you very much, and it's a pleasure to be here. I share some history with you all. I actually did my schooling near your esteemed university at the Bell campus, so I kind of know. Just another bit of tidbit here, Dr. Samir Shinde, who presented in the morning. Samir and I actually went to University of Oregon at the same time. He was my senior. So it's not only a great pleasure for me to be here, but also it's great to see some of the old colleagues that I've worked and studied with this in the past. Right? And thank you, Dr. Sriram, for this opportunity, and as well as Ganeshan. Right? So let me know if I can start and if you can see
Yeah, you may please start.
Okay, great. Thank you. So let me just kind of start off with talking about IBM Spectrum Scale, and let's step back a bit, right? So IBM Spectrum Scale is essentially, highly parallel, clustered, high-performance file system. So before I kind of get into the details of exactly, what it is and what makes it special, I think the first thing that I wanted to kind of talk about is take a little bit of a step back and say, why does it matter? Why is it important? Why are file systems important? And of course, you would have come across file systems day to day, obviously different types of file systems when you use your computer and things like that. But the thing that makes it really important and it's starting to become, so crucial to everything that goes on today is because of the data explosion that's happening. So if you kind of see this chart all the way from like 2009, when we were like, less than 125 exabytes, to 2020 now, where we're really looking at somewhere around more than 500 hexabytes, right? So there is a absolute explosion of data, right? And when you have that data, you now need to be able to store it. You now need to be able to retrieve it efficiently so that you can make use of it, right? And what's another interesting thing is, almost 80% of this data that's being gathered and stored is unstructured data. Right? So you need file systems to be able to access that data, to store that data efficiently, and of course, to be able to retrieve it efficiently so that you can make use of it in whatever applications that you need, right? So where is this, how is this data transforming our everyday life? So you go all the way from like autonomous driving, where you've got like so much data that's being gathered to train these autonomous driving vehicles, all within the context of AI, right? And then you've got like all these explorations that happen. Again, a lot of data gets used in a lot of different places. And without that today, right, we really wouldn't have like credit cards, or we wouldn't be able to have like, these manufacturing and so on and so forth, because so much of this now depends upon the fact that you gather data, you use it within for your transactional elements, but also you use it within the context of AI, right? And you basically are looking at things like when you go give your credit card, if you have suddenly, taken that credit card and you've traveled abroad and you've given it, you immediately get a text message or a call, right? Where the credit card company calls you and says, hey, we noticed some anonymous activity. Is that really you using a credit card, or is it someone else, right? And so all these kinds of things become enabled when you have data. You run AI on that data to look for patterns, and then you're really detecting what is the pattern that is expected from your previous history and what doesn't fit. And if it doesn't fit, is that a threat? Is that something that's going wrong? And so they try to basically protect you from all of these things, right? But the end result is, as this ecosystem of you using your mobile phones, you using online portals for your banking, your credit card, doing shopping online. There is so much data that is getting gathered, and these companies, in order to be able to provide the services that they provide to you, must not just acquire that data, but they must process that data, and they must process that data very efficiently and optimally. And once that data is processed, a lot of these industries mandate that this data should be kept around for further analysis or due to government regulations and so on and so forth. So within that entire life cycle, acquiring that data, storing that data, retrieving and processing that data, and then archiving that data, you literally need file systems to be able to do this job, right? And this is what makes file systems like IBM Spectrum Scale really important, right? So let's actually start talking about what is Spectrum Scale, right? What is IBM Spectrum Scale? So as I mentioned, IBM Spectrum Scale is a massively parallel, scalable, clustered, high-performance file system. So I've thrown in a lot of words. I'm sure you kind of recognize a lot of these words, right? But let me just spend a few minutes talking about what each of these things mean, right? So when you talk about a clustered file system, typically you're talking about multiple servers participating within that cluster, where they all potentially mount this file system, so that you have lots of applications that are running on all of these servers that consist of the cluster, being able to simultaneously access that data, right? So it's a number of nodes that participate in that cluster, and all these nodes have the ability to mount the file system. So unlike your, the file system that you're used to on your laptop or something like that, which is, it's got storage, you have a file system, it's only for your laptop, and it's only for that particular node, right? So the minute that you have those kinds of file systems, you don't have parallel access. But within a clustered file system, you really have that ability to have multiple nodes access that data at the same time, right? Now, next we come to a parallel file system, which is already a subset of a clustered file system. So a parallel file system is something that is really where you are taking that data and you're striping it across multiple servers, multiple disks that are attached to those servers, right? And why do you do that? And sorry, this actually keeps moving, so maybe I'll just come out of a presentation mode for a second. Let me know if this is not convenient. And maybe we'll just use this for now, right? So what does it mean when you have like you take your file, you break it up into smaller pieces, and you stripe it across all of these nodes in the cluster, and you stripe it across all of the disks that are attached to these nodes. Right? And so why do you do that? You do that for redundancy, so that in case you lose particular nodes, you still have the ability to have a copy of that somewhere else on another node, on another disk, or it's also for performance. Right? As you all know, when you read data from a disk, you have to seek to the particular point at which the data is located. You have to read it, and you have to, if you want to read another piece of data, you have to wait for that data to be acquired and then sent to you, right? But if you've got your files that are striped across all of these different nodes, you can go and retrieve that data in parallel, which makes it a lot faster. Right? So this is what parallel file systems do. Another subset of a parallel file system is something called a shared file system, right? And this is essentially where all the nodes in that cluster have access to all the disks, right? And typically this is through like a SAN environment, where each of the nodes that are serving that data as a file within the file system all have access to disks, right? And they have access to all the disks. So essentially what that means is any node is able to access any data, right? And depending on the node that you ask, it will go and it'll try to get that data back, right? But another facet of these shared file system is the fact that you typically separate out the data and the metadata. I mean, what do we mean by metadata, right? It's essentially nothing but data about, it's data about the data itself, right? What's the name of the file? How large is it? Who can read it? How many blocks does it have? Where can I find those blocks? What are the addresses for those blocks? And what I mean by that is, where is that file, that piece of that file located on the disk? Right? So this is all metadata. It's all talking about how do you retrieve that data? Where is it found on the disk? What characteristics does it have? Who can access it? How large is it? Can you read it? Can you write it? Can you execute it? So all of these things are called metadata. Right? And typically, these shared file systems tend to store metadata and data separately, so that you can first go retrieve your metadata, figure out where all the blocks are for your particular file, and then you use the actual connection to these disks on the background to get the actual data itself. That's one type of a file system. The other one is a distributed file system, where not all the nodes in that cluster have access to these disks, right? So what do you do in that case? There are subsets of these nodes in that cluster that have access to the disks. There are subsets of nodes in that cluster that don't have access to the disk. So at that point, the nodes that don't have access to the disk have to talk to the nodes that do have access through some kind of a network protocol. And they are able to retrieve that data that way, right? So it's a little bit different compared to your shared file systems. Shared file systems all have access to the disks on which the data is stored, and distributed file systems do not. They have to talk to nodes that have access, and they usually talk to those nodes through network protocols. Right? So just want you to keep in mind, clustered file systems, there's a bunch of servers that form a cluster, and they typically have access to that data. Parallel file systems are a type of clustered file system. They stripe that data across all of the disks, across all of the nodes. Shared file systems, every node in that cluster has access to the disks, and distributed file systems, not every node in that cluster has access to that disk, but it must talk to other nodes in order to get access. Right? So where does spectrum scale fit in with all of this? Right? I talked to you about all these different file systems. So interestingly, it's a combination of your shared, parallel, and distributed. Right? And the reason why we did that is because it basically allows us to be scalable, to be massively scalable, to be highly performant, and these are what our customers are really asking for. Right? And so let's kind of take a step back and see how it helps. Right? So as I mentioned, spectrum scale is a clustered file system, so it consists of number of nodes in the cluster on which the spectrum scale file system components are running. Right? So each of these nodes have spectrum scale file system components running. Some of these nodes in that cluster have access to that data, right? They may all have access to all the disks, or they may have access to only some parts of the disks. This really depends on how you configure that data. And this is where the combination of a shared file system or a distributed file system comes into spectrum scale. You can have subset of nodes that access all the disks, or you can have subset of the nodes that only have access to a certain number of disks, right? And there are also nodes within that cluster that don't have any access to the disks, and they must talk to the nodes that have access to the disks, right? So let me stop there and kind of put some names around it so that we could more easily talk about it. Any node in the cluster that has access to these disks is called an IO server, or it can also be called an NSD server, right? And any node in the cluster that does not have access to these disks is called a client, or it can be called an NSD client, right? So you have IO servers that have access to the data and the disks. You have clients that don't have access to the data, and the only way they can get access to the data is by talking to the IO servers, right? So here you can see it's a combination of your shared and your distributed, right? And where does the parallel aspect of this come in? So whenever you want to write a file into spectrum scale, right, what happens, you basically as a customer, or as a you can even do if you're on a Linux or a Unix file system, you have your VI editor, you open up the VI editor, you want to make a to-do list, right? So you start making a to-do list and you basically start writing into the file using your VI editor. What happens is spectrum scale underneath, right? Basically the VI editor will go to the file system, whatever that mount point is, and it will create that file, and it will start trying to write everything that you're writing into that file. And when it writes, when your VI application is writing into the file, what typically happens is spectrum scale is sitting on the back end. These clients are basically talking to the IO servers, and they're saying, hey, I'm getting these bits of data. Now, can you store it within your file system, right? And the minute that the spectrum scale IO servers get that data, what they do is they break that data up into smaller blocks, right? And then they distribute it across each of these IO servers. So let's say you've now written a lot of to-dos, like it's nearing your exams. You are making a huge list of all the things that you have to learn, and it's like 1 gig, let's say, right? 1 gig of data that you put into your to-do list, right? And the minute that you do that, internally, the spectrum scale IO server says, oh, I've got like a 1 gig file. Now I'm going to break these up into smaller chunks, and I'm going to write it to each of the IO servers, right? Let's say there are 4 IO servers. So it's going to take 250 meg and write it across each of these IO servers. Right? Why is that important, right? So let's say you are now trying to read that data back. You've now done with the to-do list, you've saved it, you've walked out for lunch, you've come back. Now you're trying to read it back. Typically what will happen when you try to read a file, it will first go off to the file system and it'll read the first block, right? And then once you've got the first block, then it'll go back and then read the second block. So you can only read the 4 blocks one after the other, right? You first read the first block, you read the second block, third read the third block, and fourth read the fourth block, because they're all stored on a single disk, right? This is what normally would happen. But with these parallel file systems, you're going to get block 1, block 2, block 3, and block 4 all at the same time. Why is that? Because they're spread out across all of these different servers, right? And therefore, you're able to read them in parallel. You're able to read them quicker, right? It doesn't really matter when you're looking at your to-do list, right? Because you can't read 1 gig of file content that quickly. But this becomes crucially important for high performance computing and other types of AI workloads and things like that that need to read these data really, really quickly. They need to read that data quickly, and the applications are also running on a lot of machines, so they need parallel access to your data. Right? So what does Spectrum Scale do? It splits the data so that you are now able to read faster and you're able to read in parallel. Right? So this is one of the big aspects of the advantages that Spectrum Scale has. Right? So now that you've striped your data, you've kind of looked at like where all the IO servers store the data. What happens here, right? Why is this important? Now, when the clients ask for the data to be read from these IO servers, they ask in parallel. So there's no hotspots, right? And because, and I'll explain why this is even more important. There is the fact, remember we talked about the fact that we separate out the metadata and the data. Now, when you want to read a file, what's the first thing you need to do? You need to go get the metadata. You need to figure out how big the file is. You need to figure out where all the blocks of that files are stored on the disk. And then you need to go read that, right? So here, the fact that the metadata is split and it is being served by another node in the cluster means that the nodes that are serving the data may not be the same nodes that are also giving you the metadata, which means you can now be able to take that metadata from one node and be able to ask those the data from other sets of nodes. What does this mean? Again, it means that there is no contention, there is no single hotspot, right? Let's say you had the metadata being served on one node, and there are 20 of you that are all trying to read the same file, right? What happens is each of these, you open up this to-do list, 20 of you, it's a team of people, you all need access to the same to-do list, you're all accessing the data at the same time. It goes to, if there is only a single metadata server, it goes to that metadata server and it's asking for the same information from that same node, which means that node is getting overwhelmed. It's not being able to serve that data that quickly. But when you distribute your metadata and you basically have the ability to go to different servers to get that metadata and go to different servers to get that data, you now have all of this going without any single hotspots, right? And this is what really makes Spectrum Scale be able to scale both from a capacity perspective as well as from a node perspective, right? So we literally have the ability to scale to thousands of nodes. We have customers who have 18,000 nodes within a single cluster, right? But at the same time, we also have nodes that are a single, we have a single node cluster, we have 2 node clusters, but we also have 18,000 nodes in the same cluster, which means the same software can scale from really small to really huge, and it doesn't need any extra changes. Right? So let's take a look at the different types of things that the Spectrum Scale cluster does. Right? So I know we're kind of running a little bit out of time, so let me focus on 2 things here. So Spectrum Scale can have multiple file systems, right? So you can have a file system, let's say your professors can have file systems that only they can read for their evaluations and question papers and everything that they store. So it's essentially a single file system that they have. And then all the students have another file system where you can put in your own your own data, for example, your assignments and your work and your programs and everything. These are stored on different file systems, right? But they're all stored within the single Spectrum Scale cluster. Now, these file systems, each of these file systems have what's called file system manager, right? And they can be running on different nodes. So the minute that you try to read or write a file, there is a file system manager that basically takes your requests and services it, right? It basically knows where the file needs to be stored, how the file needs to be striped. If there are already blocks of that file around, it knows where to find it. So it knows everything. But The fact that there are different file system managers for different file system means that the node that is serving the professor's files and the nodes that are serving the student's file may be completely different, right? And therefore, what does that mean? Again, you don't have contention, which means even if you've got thousands of file systems, you are now able to get the same type of performance, right? The other aspect that makes this really scalable performant is that for every file system manager, you have what's called a token manager or a lock manager. So the fact that you've got all these different nodes that have access to the disks, if they're all trying to read in parallel, that's okay. But if there are multiple nodes that are trying to write to the same file, to the same block in parallel, that's really bad, right? Because now, one person might be writing data and then another person might be writing to the same file, to the same block, and you have corruption. Depending on who wrote first, who wrote second, the data essentially can get corrupted. So how do we prevent that, right? We basically have what's called lock managers. So we take the system, and when a file is trying to be written, we take a lock, right? And this is what the lock manager or the token manager does. So it basically takes the lock and it says, okay, nobody else can write to it until I have written to it. So everyone wait, right? So what we do is we basically synchronize and sequentialize the writes, right? Why is this important that there are multiple token managers per file system? Let's say if you've got one file system and one lock manager, now every bit of that file that needs to be written, or every different file that is within that file system now needs to grab a lock, right? And if you're all going to the same token manager or the lock manager, you're going to have contention. So what we do is we distribute that as well, right? Those are running on different nodes. So depending on which file that you're trying to write to and which part of that file, which block of that file, you may be serviced by a different token or lock manager, which means, again, even if you've got millions of files, the fact that you have different token managers, lock managers, you've got a different file system manager means that you get really good performance, right? You are distributed, you are not having any single point of contention. So these are all the things that make Spectrum Scale really scalable. Like I said, it can be a 2-node cluster or it can be an 18,000 node cluster. You can serve 1 gigabyte of data, though that's very unlikely, right? But you can you can serve petabytes of data, right? So not only can you scale out with the number of nodes, you can also scale up on the disk that you attach to each of those nodes, and you also have the ability, therefore, to scale the actual capacity of data that you can store within that particular Spectrum Scale file system, right? So these are all the advantages that you have. So let's just kind of summarize all of that. The fact that we are highly scalable, we are really performant, right? We've already got the ability to like do 2.5 terabytes per second, which is already demonstrated in the field, and I'll talk about where that is. But the fact that you have all of these components, you have all of these things, you have all of these nodes, you have all of these different components running on all of those nodes, you as a customer don't need to worry about it because we allow all that to be centrally managed, and we'll talk a little bit about that, right? So it's kind of easy to manage, it's scalable, it's performant, and you can keep adding more storage as you need. So it's not like you have one cluster and then if you need to store more data, right? Now you say, oh no, you know what? It's reached its limit. Now I need to go create a completely new cluster, and then I need to now figure out how to manage both these data in these different clusters. No, right? It's a single cluster. You can scale out, you can scale up, and it's really, really robust. Right? The fact that even if you lose some nodes in that cluster, right? There's the ability to actually replicate that data, right? And we'll talk a little bit about that in the later slides. You can replicate that data, so you've got different copies of that data sitting elsewhere, Or if you've got like backend storage that can be accessed by multiple nodes, even if a node goes down, some other node has access to these disks, right? So what does that mean? We can tolerate node failures, we can tolerate disk failures, and your data is still there, right? And you can define how much replication you want in terms of how much protection do you want against loss of node, against loss of data, and so on and so forth, right? So not only are we high performant and scalable and all of that, but we're also robust in terms of we do not just go down if one node fails. Right? We have data backed up, we have data that can be accessed elsewhere, and so on and so forth. Right? So these are all the goodness of spectrum scale, right? So let me step back a little bit. This is just an interesting slide that I usually present because it talks to you about how long this has been in the field. Right? So spectrum scale first got developed in 1993 as part of IBM research, it was called GPFS at that point, General Parallel File System. But what has happened is, typically you find like a product will be created, will be developed, it'll be going out into the field, but through time, right, you'll see, well, it can't meet the needs of all these new applications that are coming in. It can't meet the needs of all these different, different ecosystems, different environments. So what tends to happen is, that product will die, and then a new product will be created to kind of do all the things that are needed, right? But spectrum scale was so groundbreaking when it was created because of all these issues that we've talked, all these things that we talked about in the previous slide. It has lived from 1993 all the way here, and it has continued to evolve, right? It started out as only a POSIX file system. Now it has NFS file system capabilities, it has SMB, it has HDFS. It now is in the cloud. It serves containerized workloads. So it has grown. It has really been able to kind of enhance itself all these decades, right? And interestingly, I was kind of talking to another colleague of mine, which also kind of brought out that not only is this product being able to do so many different things, but it retains the fact that the core capabilities that it has: scalable, performant, robust, right? Even though it's doing all these different things. And we'll talk a little bit about that later in the slide deck. So let me kind of take another turn and say, now we've talked about what is spectrum scale, why is it good, why is lived for 20 years. Now let's talk about who uses it, right? And like if you look at it, so again, these are very interesting because you have, I think right now we've got more than 4,000 customers in the field that use spectrum scale. And like I said, they have very small clusters, they have huge clusters, right? But not only that, if you look at the typical customers that run us, right, like 57 of the global 100 run companies in the world run spectrum scale, right? 57 of the biggest companies globally run spectrum scale. 9 out of the 10 automobile manufacturers run spectrum scale. Investment banks, right? 9 out of 10 run spectrum scale. 18 out of the top 25 banks run spectrum scale. 8 out of the top 10 global retailers and top 5 insurance companies all run spectrum scale. So on this end, you have all of these companies that are running spectrum scale, right? So that's great. On the other end, you have I think Samir touched on this a little bit in the morning. You have what are called these choral systems, which are supercomputers that were built for the Lawrence Livermore National Laboratories in the US, as well as the Oak Ridge National Laboratories, right? And so these systems were called Summit and Sierra. They are IBM systems. They make use of IBM power. they run Spectrum Scale internally, and they were the fastest fastest supercomputer that was available in 2019, right? So this kind of goes to show not only are all these really big companies running it, but high performance needs of these supercomputer users are also being met by Spectrum Scale. So it's all things to all people, right? That's kind of the way the way you can think about it, right? And that's its strength, and that's why it has survived for 25 years, and it's still going strong. So let's talk a little bit about what are the other features, right? We talked about the internals, we talked about the customers. Let's talk about some of these other internal features, right? That Spectrum Scale has, and it kind of goes back a little bit to why it has lasted in the field for 25 years. Right? So when we started, as I showed you in that history slide, 1993 we started, and it was essentially a file system that was POSIX compliant, right? So the POSIX compliant file system was what we first pushed out. But then our customers started using a lot of other file system serving protocols like NFS and SMB that you may have heard about. And so we built that into Spectrum Scale, right? And one thing that I want to note is there are other products that do this, right? They serve POSIX workloads, they serve NFS workloads, they serve SMB workloads using all of these different protocols. But typically what you tend to find is you have data that is being stored in different places to allow these different protocol accesses, right? So whether it's an NFS client or an SMB client, you may actually be storing that data differently. But Scale is not like that, right? You store the data once, and whether you want to read that file or write to that file using POSIX semantics, or you want to write using NFS protocol or SMB protocol, it's a single copy of the data, right? You're not storing it differently depending on the type of different protocol that you need to access it through. So what that means is, and this will become very important as we talk about AI workloads, right? So you're storing your file only once, but you're able to read that file using different protocols, right? And so then, okay, some time went along and our customers were very happy with the fact that we were able to do POSIX and NFS and SMB. And then the whole Hadoop environment just mushroomed, right? And all customers started going towards using Hadoop, and Hadoop has its own native file system protocol called HDFS, and has an implementation of HDFS, right? Which is a file system on its own, right? But it's catered towards Hadoop workloads. So what did we do? We said, oh well, our customers are now wanting HDFS. Let's build that protocol into Spectrum Scale, right? So now we've enhanced it with HDFS, right? So now Hadoop workloads can also access data that is stored within Spectrum Scale. And again, it goes back to the fact that, hey, you're still storing only one copy of the data. You might have written that data through POSIX semantics, or you might have written that data through NFS, but now you can read that file through HDFS, right? Same file. So as you're making changes, you can read, right? So really shows the rich set of features, right? Then, about the same time, OpenStack came along, right? And I think many of you may be familiar with OpenStack. So they have things called Cinder and Glance, which are, again, types of storage serving capabilities within the context of OpenStack. So we said, oh, well, we should support that as well, right? So we supported that. Then came along Object, right? Object file systems. And then we said, well, we can do that too, right? So not only do we have all these other protocols, but we can serve object protocols. So single copy of data being able to be accessed by all these different protocols, depending on what needs you have. Whether you're running AI workloads, whether you're running OpenStack, whether you're running object type of workloads, you're running Hadoop, you're running your normal HPC POSIX type of access, we do all of it, right? And internally, we support multiple storage devices. We support flash, we support spinning disk, we support tape, we support, like all these different types of configurations of that. Why is that important, right? So data is expensive to store depending on where you store it. Flash is very expensive. Flash doesn't have the same kind of capacity that tape does, right? But it's very, very quick. Spinning disks now have huge capacities, but they're not as fast as flash to retrieve and write. Tape, massively scalable. You can write so much data into tape, very, very slow, right? So we have the ability to internally attach all of these different things into the file system at the same time, right? Why is that important? So suppose there are files that you are reading today, right? You want it to be really, really quick. We have the ability to store all these files in a flash drive, right? You can write to it really quickly. You can read to it really quickly. It's right there as you want it. But let's say these are all data that you stored like 10 years ago, or let's say it's 2 years ago, and you don't access it as much. Maybe you access it once in 2 days, once in 3 days. So what we at that do is, at that point, we can take the data that was stored in flash and we can move it to disk, right? So now we are basically tiering data from your really fast storage where you need it really quickly to saying, well, you know what, we'll store it on disk because the customer is not using it so much. So we'll store it on disk. And then let's say it's been 5 years and now you hardly ever use that data, but you still need that data to be around. We can migrate that data into tape, right? And tape, you can store huge amounts of data, and let's say all the projects for every student that has ever entered your university, all you can put it on tape, but you might not need it. But if that person comes back 10 years from now and says something like, you know what, I need that particular file, it's still there, right? But it's just very, very slow to be retrieved. But this way, we can cater to what kind of access you're doing, how quickly you need it, and how much you've used that file. And we can automatically tier it to different storage based on policies that you've already set, right? So these rich set of features are also there. On top of it, I won't spend too much time, but you have the ability to encrypt data because it's becoming really, really important to make sure your data is secure. There are so many breaches into environments, and if you've just got your data stored as it is, anybody who breaches that data can then get hold of it. They get your mark details, they get your assignments, they get everything. They can do anything they want, right? So we provide encryption facilities. We also provide compression facilities because you might want to compress your data before you store it because you've got so much data, even though you've got tape, you've got disk, you've got flash, there's just too much data that you have. And we compress that data, we store it, and when you want to retrieve it back, we automatically uncompress it and give it to you, right? So this is the ability to have the same amount of storage, but store more data within it, right? So these are all, again, things that Spectrum Scale allows you to do, right? We'll talk a little bit about something called AFM later. I'll talk to you when we get into more of the cloud scenario, right? So let's talk about the different use cases. We know how, all the goodness of Spectrum Scale. We know all the functionalities. Now let's bring it back in, where do our customers use it, right? And I told you about all the different customers that we have. So how do they use it? So the first thing is, we are really good at being the file system for AI, right? So why is that? Let's look at, why is it that we are good for artificial intelligence workloads, right? So the first thing is, you have various different cycles within AI, right? And we'll talk about it. It's the ingest cycle where you're literally, maybe you have IoT sensors, like when you talk about your autonomic driving, right? Your cars have huge number of sensors. They're all like reading these, huge amounts of these sensors. All of this is data that needs to be put into a particular file system. And once it's ingested, then you need to prepare that data, right? You need to be able to figure out, like, how do I, you do analysis on that data to say, look, what are the outliers, what are the pieces of data that doesn't make sense, what's bad data, what's good data, what is the data that I care about, so you do all of that preparation, right? And then the next phase really is, once you've got that preparation done, then you train your model, right? And then once you train your model, then you go off and then you say, I want to run this model in production. So, you've now taken a model, you put it into your car. Now, as the car is getting fed all of this information from its sensors, these models are automatically executed. And a minute someone walks in front of the car, the sensors are seeing it. Then the model that you've already created determines instantaneously that this is a person that's just walked in front of your car. Then the minute that the sensors detect that and the model detects that this is a person, the model knows the type of action that it needs to take. So it needs to apply the brakes. It needs to make sure that it pulls itself out of gear. It does all of this, right? And so that's when the actual model is being executed. All of this needs storage, right? But typically when all of the storage comes in, they come into different file systems because not one file system is good at everything like we are, right? So there's some file systems that are really good at high, catering to that IoT data that's coming in. It's able to take that data and store it really quickly. Then there's, file systems that are really good to aid the preparation because you need to be able to access that data in parallel. Training, especially if you've got neural networks and things like that, these are GPUs that need lots. I mean, GPUs are expensive. They read data at enormous speeds, right? So they need parallel file systems, right? So there's different file systems that typically customers run. But when you have Spectrum Scale, it's a single file system that can serve all of that. So it's really, really suited to all of these AI type of workloads because we allow the ability to store data in one place and access through different protocols, right? And I'll kind of talk about that here. So when you look at this, right, I talked about the ingest phase, right? So ingest really requires high throughput. It needs to land on file systems that are like really, really quick. They're able to store the data that's coming in at enormous speeds, right? When you think about that car, that IoT sensors are detecting millions of data points each minute, right? And that needs to come into the file system and get stored. So this is where Spectrum Scale is really cool because you can now have a flash type of a file system there, storage where data is being, ingested in really quickly. But then when you go into trying to classify that data, prepare that data, make sure you kind of look at all your analytics and say this is good data, this is bad data, this is outliers, these are data points that I want to use. All of that, again, same file system, but you might be using some Hadoop elements to access it, which means the initial data in the ingest period came through POSIX. Now you're trying to prepare that data. That typically goes through HDFS because you're running within a Hadoop environment. And then now you're analyzing that data, right? You're running your training on it. Now, the minute that you're running your training, what does that mean, right? You've got GPUs if it's a neural network. You now again access that data through parallel POSIX type of access. Again, Spectrum Scale does POSIX, does parallel access, right? So what that really means is you still got only one copy of the data, but you're able to now serve it really quickly. Now, suppose you didn't have this. Suppose you had another file system, so you'd have to ingest it into a really fast file system. Then you have HDFS. So you have to copy the data from your original file system into HDFS. Then you do the preparation. Then again, you need parallel POSIX access to do analysis during your train phase, right? And your inferencing phase. Then you have to now move that data again to another file system, which is good at doing that. You've got 3 copies of data now, right? And if you change one copy of data at some point, you now have to recopy that data everywhere, right? So you now start having more and more copies of the data. you don't know how, which is true, which is not true, which data is most recent, which data is not, which data has what, so it's really confusing. But with spectrum scale, all of these things become very, very easy to do. So let's look at, okay, so we talked about why spectrum scale is really good for artificial intelligence. Now, with the whole cloud computing that came, right? When things started, you had a lot of customers that 20 years ago, maybe even 10 years ago, you had lots of customers who ran everything within their on-prem data center. Like every company, like all of these big companies, like Facebook and Google, and they all had their own data centers on premise, right? So they would build a data center. They would have all of these computers, these storage devices built within that data center, and then now they will manage their data internally. But as cloud computing became more and more prevalent, instead of building your own data center, right, which customers still do, but you can now, let's say it's coming up where you have the holiday season like Diwali, right? Diwali is coming up. So now you know that more customers are going to hit your retail site when Diwali is coming around the corner. Let's take Amazon, for example, right? The amount of traffic that happens on Amazon during Diwali is probably a lot more than other times of the year. But they can't buy, a company cannot buy more servers and more storage just to serve that 1 week or 2 week period in a year. The rest of the year, that data is lying. I mean, those servers and storage elements are lying idle, right? So you don't want to do things like that. What cloud allows you to do, it allows you to pay for something like a server or storage elements at the time that you need it. You get it provisioned, you use it, and then once you're done, you say, okay, I don't need it anymore. You give it back, right? So they save on cost. They save on expanding their data centers and maintaining it and so on and so forth. But it's then important that whatever data that you have be able to go between your on-premise environment and your cloud environment, and it's able to go through securely, right? Because when data is traveling across the network, if someone is looking at that data, you shouldn't lose or compromise all that personal data and important data that is going across the wire, right? So you need data to move from your on-premise to your cloud environment, but you need to do so securely, right? And how does Spectrum Scale help? So the first thing that you notice about Spectrum Scale is this software can be run on-premise within your data center, but it can also be run on the cloud. We already have offerings on AWS. We have work going on Azure, IBM Cloud, Google Cloud, Oracle Cloud, and Alibaba Cloud, right? I've talked about here, AWS is already offered. IBM Cloud is a managed service that is getting offered. Oracle Cloud is something that is a business partner that we look at. Azure is something that we have a business partner that's already doing that. Ali Cloud is something that we also offer through. So it's available in all these different clouds, right? So you can actually go to AWS Marketplace. You can provision IBM Spectrum Scale, and you can create your own cluster there. Right? And how is this important, right? So before I talk about how is it important, you can actually look at how do we deploy IBM Spectrum Scale on the cloud, right? And we do it using certain tools like Terraform and Ansible, right? So we use Terraform to basically provision VMs, disks, and so on and so forth on the cloud. And then we use Ansible to set up and configure IBM Spectrum Scale there, right? So the combination of Terraform and Ansible, we're able to automatically create a cluster on the cloud, right? And so, for example, if you go into Amazon Marketplace and you just say, hey, I want a spectrum scale cluster, it'll ask you a few questions like, do you want to create it? How much capacity do you want? How many nodes do you want? What kind of replication do you want? Do you want it within a single virtual private network, or do you want it, or do you want it across different availability zones and so on and so forth? The minute that we ask these questions using Terraform and Ansible, we're actually able to create a spectrum scale cluster on Amazon, within the Amazon environment, right? And all these types of code, the Terraform code and the Ansible code, it's already open sourced, right? We've open sourced it. You can go to these Git repositories. I can send you the link later. You can actually go to it and look at our code and look at what do we do to set up spectrum scale, to actually deploy spectrum scale within the cloud, right? And so this will actually, if you look at that code, it'll give you some background into exactly how is all of this happening, right? So now it's good. We've got like a spectrum scale cluster that's already created on the cloud. That's great. Now, the scenario that we went back to, right? You've got your on-premise data center, you've got your servers, you've got your storage, you've got huge amounts of data that's already stored, and Diwali is coming. Now, the minute that Diwali is coming, you know that you're going to need more servers to be able to serve all the traffic that's going to hit your website. You know that you're going to generate more data. So how do you take some of that data that is on-prem and move it onto the cloud? And what about the data that is getting created on the cloud? How do you move it back into the on-premise environment? Right? This is what we call the hybrid type of a cloud, right? So you've got some data which falls within the context of your on-prem. You've got some data that falls within your cloud. You need to have both of these things communicate with each other so that you are able to effectively do all the work that you need, right? So for example, another example I usually give is, right? Like, so you've got a lot of data that is on-prem, right? So this, let's say, again, go back to a retail customer. You bought a lot of things from this retail customer, and every time you buy, they save that data, they keep it in their on-premise environment. Now, this data, when it's coming to Diwali, right, they want to take that data, they want to look at what have you bought in the past? What is it that you're likely to buy now? So they want to then pitch that to you, right? So when you go to your retailer website, they say things like, hey, you bought this in the past, you might like this, right? So now, in order to be able to arrive at that conclusion, you now need to take that data and you now need to rapidly analyze it using AI, and you need to be able to inference it saying, okay, this person has bought XYZ product. Now they're likely to buy this other product. And so they suggest it for you, right? So all of these things can be done, especially when you've got a lot of customers that are coming in during Diwali. You can take a subset of that workload, you can move it onto the cloud. You can dynamically provision spectrum scale on AWS or other clouds, like I've said, and then you can run your application on that cloud, and you can analyze that data so that it scales to the demand. And once that demand is gone, once Diwali is finished, right, and everyone's bought whatever they need, you can just shut it down. But the important thing is spectrum scale runs on the cloud, spectrum scale runs on-prem, and I'll tell you about an ecosystem that allows you to kind of share data across cloud and on-prem. Right? And now we go back to this hybrid cloud that I was talking about. Data is on-prem, data is on the cloud. How do you move the data around? How do you share that data? Right? So spectrum scale has this unique feature called active file management, right? which is this caching technology that you can use, which allows you to cache your data across huge distances. So let's say the cloud, wherever the cloud that you're using, the region of the cloud that you're using is in the UK or is in the US, but your customers are your on-prem data center is in Mumbai, let's say. Right? So you've got your data in Mumbai, you've got your newly provisioned cluster on in UK or in US, because that's where your customers are. Like, let's say a lot of your Diwali customers are, you've realized that they're going to access data, or they're going to buy products from there to ship to their families at home, right? So now you've got a newly provisioned cluster in the UK data center of this cloud, and you've got data on-prem. Now, how do you, flow the data between these two spectrum scale clusters? And that's where AFM comes in, the active file manager, right? So here you have the ability to write data into one cluster, let's say into your on-premise environment, and behind the scenes, that data will actually be synced up to the cloud. And when you write data onto the cloud, behind the scenes, that data is synced up to the on-prem environment. Now, why is this so good, right? This is so good because typically, when you are trying to do this kind of data access from multiple environments, if you are doing it synchronously, right, which means you write the data and that write does not return until all the copies are written to on the cloud and on premise, then you have a real problem, because the latency of how long it takes to go through the network is huge, right? So when you want to write, you have to now wait for that write to go all the way across the UK data center, write, and then be acknowledged before you can tell your application, I've written the data. That's really bad, because the response time now on your website might be terrible, right? So you ask for a product, it takes like 40 seconds to load the page, or 50 seconds to load the page. That's clearly not acceptable, right? So what do? Here, you write the data on-prem, or you read from the data on-prem, and internally, asynchronously, right, that data is getting stored onto the cloud, or from the cloud onto the on-prem environment. So this AFM technology is really good at when you have a lot of distance between your wherever you're storing data. You're trying to sync that data asynchronously, and you're also trying to do it over a slow network, right? And AFM is able to handle all of that. And that's the real critical technology that we use to allow this hybrid cloud environment to exist, right? So let's take a look a little bit further into some of the other things, right? Like this this AFM technology is not just about on-premise and cloud, right? You can have one on-premise data center in Mumbai, one remote site, let's say in Chennai, and a third, spectrum scale cluster on let's say the UK and US regions of a particular public cloud vendor. Now you can use AFM across all of these sites to sync up your data. Right? In fact, we have a customer right now. What they're doing is, and this actually happened because of the lockdown, right? So they had a data center in the US, and they had multiple employees that were accessing that data center. But what happened is, when the lockdown happened and many of their employees got stuck in different parts of the world, right? Like some got stuck in Australia, some got stuck in India, some got stuck in the US, some got stuck in the UK. They were all trying to access this data for development purposes from their on-prem data center, which was in the US, right? And so the latencies were like huge, and their employees weren't able to be really effective. So what they did was they very rapidly provisioned spectrum scale instances on different clouds, including one, potentially in India, one in the UK. I'm just giving these as examples, right? But they were able to do that, rapidly deploy spectrum scale on it, using that automation infrastructure that I talk about, and then using AFM, be able to sync up your data so that when these employees who are sitting in Australia wanted to access the data that was stored, they didn't have to go to the US data center. They just went to their nearest cloud region, right? So if there was a cloud region in Singapore, that was the data center that they would access. Or if there was a cloud data center in Australia, that's even better, right? So AFM allows you to go across all these on-premise and all these cloud data center. It syncs up that data so that even though you have the data that gets generated or written to in one place, it can now be accessed from all of these different places. And even if you write on the cloud, it can then be synced back onto the on-premise data center. So this really provides this ability to share your data across all of these environments. Now, the last thing that I want to also talk about AFM is, we talked about S3 storage, right? Object storage. Now, a lot of these public clouds have very cheap object storage, and they are a lot cheaper to use compared to, like, disk storage or your SSDs or flash drives or so on and so forth. So what a lot of our customers are saying, and remember, I told you about like this ability for Spectrum Scale to look at your data and look at how much it is accessed, and then be able to move it automatically from a flash, to a spinning disk, to a tape. Now you can also, using AFM, move it to your S3 storage on the cloud. Right? So you now have this ability to take your data, whether it is on the cloud sitting within a Spectrum Scale cluster, or you have data which is in a Spectrum Scale cluster on the actual on-prem environment, and be able to take that data and write it to the object store, the S3 compatible object store that is on the cloud. You can write to different cloud object stores. You can write to Azure, you can write to AWS, you can write to all of these different types of S3 object stores that are there. You can also write to object stores that are on-prem, like IBM offers its own object store products, right? You can write it to it on-prem. So the fact that you have now AFM allows you to share data across all of these different clusters, but also allows you to put that data into your S3 storage on the cloud and access it, right? So these are all the advantages of a Spectrum Scale cluster. Right? So let me kind of, I think we probably don't have a lot more to cover. Let me cover this, and then I saw there's like a couple of questions. I will try to get to those questions as soon as I'll cancel those as soon as I can finish this presentation. Right? So okay, so we talked about the fact that Spectrum Scale has all these great features. It can be used on premise. It can be used on the cloud. Now we are looking at the brand new type of workloads that are coming, which are really containerized workloads. Right? And Samir, in his presentation today morning, talked a little bit about what are containers, why would you use containers, and a lot of our customers are now taking their applications, containerizing them, and running them as containers. So that immediately means, hey, if you are running your application as a container, these containers need access to data, especially persistent storage requirements that some applications have. Right? So the minute that you have these applications that are running within the context of containers, now you need to be able to access that whatever data that you want from this container. Right? And so here again, even though Spectrum Scale did not have this functionality when we started, we have now built that functionality about 2 years ago. It's now in the market, where using Spectrum Scale, you can now also access this data for containerized workloads. Right? Okay. So there are two ways that you could actually use this. Right? The first is, okay, why is this slide not coming up? Yeah. So there are two ways. One is there is something called a CSI, which is a component which allows containerized workloads that need access to persistent data to use data stored within Spectrum Scale. Right? So this is, you can almost think about it like yet another protocol, just like we talked about POSIX and NFS and SMB. Now we have the CSI that allows data to be accessed from your containerized workloads, right? So this is just one part of it. So what we did was we built the ability for containers to access data that is stored within Spectrum Scale using the CSI component, right? So again, same thing. You had your data stored once, but you're accessing it through different protocols, right? But now, if you are a customer that has taken all your applications and you've completely containerized all of them, and let's say you're using something called an open, like some example like an OpenShift environment to manage and deploy, install, and upgrade all of these containerized applications. These are orchestration and management frameworks like OpenShift and Kubernetes that allow you to do that. Now, you have containers that are your application containers that are running within this context. And you want to access data, right? Now, as I said, you can use the CSI to access the data that's already stored in Spectrum Scale. But as you know, when we talked about Spectrum Scale on-premise, it can run within the context of just bare metal systems, or it can run within a VM that is running on the bare metal system. Same thing on the cloud. It can run on the clouds that offer bare metal support. It can run on bare metal. And of course, it can run on virtual machines, right? So now you have a containerized environment, but you don't want to maintain a bare metal environment or a VM-based environment just to be running Scale. So you want Spectrum Scale itself to run within the context of these orchestration and management infrastructures like Kubernetes and OpenShift. So what we have done is we have taken Spectrum Scale and we have containerized Spectrum Scale as well. Right? So you can access the data that is stored in a VM-based Spectrum Scale. You can access data that is stored on a bare metal-based Spectrum Scale. But with this new evolution, you can also take Spectrum Scale that is running within the context of a container, and you can access the data. Right? So again, like I said, as the ecosystem has first moved from bare metal to virtual machine to containers, the Spectrum Scale file system has evolved to keep up with all of these things. Right? So let's talk about I'm not going to spend too much time here, but I did touch upon this earlier. The fact that Spectrum Scale has all these different components, has all these different abilities to kind of have different types of storage. All of this needs to be managed, right? It needs to, when you want to add more disks, when you want to add more nodes, when you want to kind of look at the health of your system, when you want to look at the throughput and the latencies that you're seeing, how do you do all of this, right? And we attempt to make it easier for you by having a single pane of management, and you can do that through a GUI tool that we offer. This is a Spectrum Scale management GUI. It allows you to do all of these day two operations for management. And like I said, it allows you to just look at the health of the cluster, add capacity, add nodes, enable, disable features, create new file systems, create new file sets within the context of file systems. So all of this management can happen through either your management GUI, or it can happen through a CLI. It's the same functional CLI equivalent, or it can also happen through REST APIs. So why is this important, right? So for customers who are more comfortable with the GUI, they can access the GUI. For customers who are more used to the CLI, they use the CLI. And the REST APIs can be programmatically invoked from your application, right? So for example, this is kind of an example that we've had some people try to do, right? So you can actually, let's go back to that Diwali example, right? So you're now seeing a lot more traffic coming in, and you don't want an administrator sitting there to be able to say, hey, I want to be able to I want to create this new cluster on the cloud. I want to then be able to automate that configuration of that cluster. I want to be able to then use AFM to move that data. And then I want to be able to, set up another file system there. And then again, set up AFM in such a way that it syncs up all my data. Now, you can automate all of that through the Terraform templates and the Ansible playbooks that we've already provided to create a new cluster on the cloud. And then using these REST APIs, you can create file systems automatically on the Spectrum Scale cluster on the cloud. And then you can set up AFM, and then you can basically sync all of that data, right? And that's why REST APIs are important, to be able to programmatically, invoke all of these things. And one other thing I want to just quickly mention here is it's really important to be able to monitor the health of these systems, right? You don't want to, you've gone for the night, you're an administrator, you've gone for the night, and you don't want to come back next morning and find out that 10 servers in your data center have crashed because there was a huge rain, there was a flood, it flooded your data center, and all of that is gone, right? So Spectrum Scale gives you all of this ability to send events, right? So you can get SMSs, you can get other types of notifications when the system detects that there are certain nodes that are failing, there are certain disks that are failing, and so on and so forth, and it will immediately alert you, and then you can take course-corrected actions. Right? So these are all the management goodness that we give you, right? So lastly, I want to talk about one more thing, right? So we've talked about Spectrum Scale as a software that runs on bare metal systems, as software that runs on your virtual machines, as software that runs within your containerized environment. And now we're going to look at a Spectrum Scale integrated solution, right? So this is a combination of the software plus IBM's hardware, which gets packaged all together, so that you don't have to now take the pain to basically order your server, bring it in, connect it to the network, install operating system, take the Spectrum Scale application, be able to install it, do all the configurations that you need, and then you are able to access that data. That's a lot of work, right? A lot of customers do it because that is one way. But if you want to just buy one appliance, right, that basically has all of the servers, all of the software, all of the disks, everything combined, we have an offering for that too, and that's called the ESS, or the Elastic Storage System, right? And that's an integrated system of hardware, software, networking, everything packaged together as just one thing. Okay, so let's look at what that looks like here. So these are some pictures of different, these elastic storage systems that we have. There is what's called the 5,000 range. There's also a 3,000 range. They have all the goodness that Spectrum Scale offers because, internally they're running Spectrum Scale software as well as all these other IBM hardware elements, right? And if you look at that supercomputer that I told you about, we actually deployed Spectrum Scale elastic storage systems within that. And because it's a single integrated system, we're able to give you really advanced capabilities like high performance, ease of management, and this ability to just buy this box, put it into your data center, and just use it, right? But one more thing that becomes really important is when you are accessing data, right? I think many of you would have heard about RAID, right? So, RAIDing capabilities are ways that you can protect data from disk failures, right? So what you do is you can either take the data and you can just copy it to multiple disks, or you can take the data and then you can say, I'm gonna, as we talked about before, as you write the block, you're going to now compute a parity, and then you're going to store that parity separately. So in case a disk is lost, using that parity, you can recover that data. Right? So this gives you one more ability to tolerate failures. Now, when you have enterprise storage systems, like IBM has a lot of enterprise storage systems, and they will have this ability to do RAID, right? But if you didn't want to do that, you can also do RAID as software, and that's typically what we do within this ESS, system. That is, as I said, the integrated offering. So when we do software, software RAID, we do something called erasure encoding. We basically break up the data so that we can store it in multiple places. We compute parity. We store that parity so that in case there are different types of failures on your disk, we can recover that data by reading parts of that data, reading the parity, and then be able to regenerate that data, if you will. Right? So this is something that is already inbuilt into the IBM Spectrum Scale ESS system that I just talked about. So these are just some pictures of these ESS systems. This is the 5,000 range, which is really the capacity range, allows you to add a lot of storage capacity. This is the ESS 3000, which is really built for this ability to do very quick access. This has all flash drives, and this has all spinning disk drives. And you can kind of look at what are the type of access speeds that you can get, and so on and so forth, right? So these are systems that are meant for speed. These are systems that are meant for capacity, right? So these are different variants of the ESS themselves. And so finally, I've finished with my presentation, but let me stop sharing, and I'm going to attempt to share a quick demo, right? Let me try to do that. Can you, sorry, stop sharing again. Okay, so this is a Spectrum Scale cluster. Can you see my screen?
Yeah.
Okay, yeah, thank you. So this is a Spectrum Scale cluster that I just installed on VMs within our development lab. And if you look at it, like there are some commands. I'm not going to like get into the exact details here, but let's look at, like I told you, that this can have multiple nodes in the cluster. Right? So if you look at it, this tells you that there are 4 nodes in the cluster. And as I said, these 4 nodes, some nodes serve as manager nodes. Remember, these are the file system managers. These are the token managers. They act as that. There are some other nodes which are acting as NSD servers or IO servers. So these 2 are the only servers in my cluster that have access to disks. Right? These 2 nodes, like the Sharkworm 1 and 2, do not have the ability to access disks. Only these 2 nodes have access to disks, right? But these 2 nodes are running components that will allow you to run NFS and SMB. And this node is running my management GUI that I talked to you about, right? And these are all x86 VMs that are running RHEL 7, right? Red Hat Enterprise Linux 7. And these are, like I said, these are 4 nodes in the cluster, 2 IO servers, 2 client nodes, 2 protocol components that are running on. And what all components have I got, right? You can actually tell what are the different types. Right now, I've disabled all of these just for ease of purpose, but I can enable any of these like NFS or SMB or any of these things, right? But these are all the nodes that I actually have in my cluster. Right? Then let me take a look at what are the file systems that are there in my cluster. Sorry, MMLSFS. So there, it's telling me that there are 2 file systems. So there is a file system called FS1. There is a file system called shared root. Okay, so if you now look at your system, right, and you do a DF, now it will tell you that this file system FS1 that we saw earlier is mounted on a path called IBM FS1. And then this says shared root, that's a different file system, is now on another mount point called IBM says shared root. So let's go there, right? Let me just go into that file system, right? So is there files? Yep, there are 2 files, right? So this is a file called bar, and oops, it doesn't have anything. This is a file called foo. So oops, cat foo. Again, it's got nothing, so I should put something in there, right? So I'll just say something like this is foo, and I'll write to that, right? So what can I see here? I can see the contents. This is foo, right? So this is on one of the nodes in that cluster. This is VM1. Let me open up another terminal and let me go to another node in the cluster, right? Just taking a little bit of time. So I'm going to log into another node here. So now I'm going, oops, sorry. I'm going to this VM2, right? And now if you do a host name, just to make sure it's VM2, right? Now, if you do a df -h on this guy, you can also see the same file system is mounted.
For the VM2, the screen is not visible.
Oh, I see. I'm sorry. Let me just share it. I'll stop sharing and sorry about that. So this is this is VM, let me bring VM2. So now let me just clear it and show you again, right? So this is the host name. So you can see that this is VM2. Now, if you do a df.
No, sir, it's still showing as VM1 colon FS1.
Oh, okay. Let me just
The
share my.
That you had cat foo.
Okay.
That's a screen that I'm able to see.
I see. Okay. Let me just stop sharing for a second, and let me share my entire screen.
Yeah.
Can you now see?
This is fine. Yeah.
Okay. Excellent. Okay. So now I logged into VM2, and I see that it's the same here, right? So the file system FS1 is also mounted here. So if I go to that file system, I can again see bar and foo. And if I were to read the file foo, it's still the same content, right? So let me read bar here. Originally, remember that bar didn't have anything, right? So let me now write something into that, right? So this is bar written from VM2. And let me just put that into bar. Now, if you look at the content of bar, this is what it says, right? This is bar written from VM2. Now, I can go back to VM1. And can you see that now?
Yeah.
Okay. So now, if I do foo of bar, you can see that now you are able to see bar. Originally, nothing was in bar, right? Now you can see it even though you wrote it from the other node. And now I just noticed that bar has the content of bar has a spelling mistake. And by the way, I did not do it on purpose, but I just noticed that there was a spelling mistake. Instead of from, it says from. So I'm going to change that, right? And I'm going to write it out again. Now let me cat bar again, and you will see that the spelling mistake has been corrected. So now it actually says from. Let me now go back to VM2, right? And you'll see that the host name is now VM2. If I do a cat of bar again, it's now got the change spelling, right? It was FRON, now it's FROM. So this doesn't tell you about the full power of the spectrum scale system, like, you'd be doing a lot of parallel access, huge files, files that are 1 gig, 2 gig, 3 gig, 10 gig, 100 gig, so on and so forth. But this is just a quick example of some of the things that you can see, right? And as you can see, like, you can see that I showed you that there is 4 nodes in the cluster. Like, there's 4 nodes. You can also like check what is the state of each of these clusters. Is it up? Is it running? You can use these CLI commands to actually shut down servers, start up servers, create file systems, so on and so forth. So all of these things can happen. But let me stop here. I think I've gone way over time. So let me stop here just to see if there are any questions.
Yeah, thank you, Muthiah sir. If I have one question, is spectrum scale free for academic institutions?
That's a great question. Actually, I kind of meant to put that into my slides, but I did forgot. There is something called a developer edition, right? And I'll work with Ganeshan to kind of get you that link. What a developer edition is as long as you use it within an academic environment or a non-production environment with certain limits on capability and certain limits on the storage that you use, you can actually download that software and you can play with it, right? There are restrictions about what you can do and what you can't. It cannot be used for anything other than just being able to look at it and explore it, right? You can't run it as an enterprise file system that is serving your data, or you can't like exceed above a certain capacity. But as long as you adhere to those licenses, it is freely usable, and I can share that link.
Sure, thank you. And I have one question from one of the attendees that so the file that was created at one VM is accessed at another VM, and you are able to modify it. Won't there be a violation of the privileges of users and group members?
Absolutely, and that's where all these file permissions come in, right? So in both of these, I mean, I kind of cheated a little bit, okay? So these systems are development systems, and so they're not hooked up to like a real enterprise grade system where you can define privileges for each of your users. So you can say something like user X can read file system, a particular, they can access files in that file system. And within that file system, you can also define who can write to it, who can read from it, and so on and so forth. So all those access permissions are there. And you have the ability to, using enterprise grade tools to sync your users across all of these different nodes. Here I cheated a little bit because if you look at who I am, right, you'll see that I logged in on VM2 as root, and if you see here, I am root, and I am basically saying that in my test system, the root here and the root on VM2 are the same roots, right? Typically, that will not be the case. Yeah. You will now, you will not have that. But here I just kind of cheated and said both are the same users, and I configured my system so that they are the same users.
Oh, that's not a kind of cheating. That's to demonstrate the capability of the system, how the files move across VMs and are rather accessible across VMs seamlessly. That is what you intend to demonstrate.
Correct. I actually, if I had a little bit more time, my thought process was to use like a different users that actually are served from, let's say, some other, something like a name server or something like an LDAP environment or something like that. And then you will be able to see that, if you are a different user, then you wouldn't be able to access that file. You might be able to read it and so on and so forth. But I didn't have time to set it up, and I do apologize.
Muralidharan, you had raised your hand. If there are any questions, can you please type in? D. Muralidharan. Or by mistake had you raised your hand? seems that he has by mistake clicked on the raise hand.
Okay, sure, no problem.
That being the case, let's end up this session. Thank you very much, Muthiah sir, and it was really an insightful discussion on spectrum scale. And I mean, I'm sure that a lot of students and the faculty members would have got the understanding about spectrum scale. So, and something that was awesome was on the hybrid cloud part. So have some of your data in the private cloud and then offload some of them on the public cloud, and then how you seamlessly access them. So that was really a beautiful use case that you explained. And thank you very much, sir. I really appreciate your time and effort in spending time with us. Thank you very much. As soon as the relaxations are there post-COVID, we would like to have you physically in campus and we'll have an one-on-one session with our faculty members. Thank you.
Absolutely. Yeah, thank you so much for the opportunity, Dr. Sriram. And as soon as I get the opportunity, I would love to travel. Thank you.
My pleasure, sir. Thank you.